In this video, we will discuss the fourth and final type of conic section. Get ready, the hyperbola. So remember what the definition of a conic section was? You take a double cone, you slice it at various angles with a plane, and you end up with one of four conic sections. We've done the circle, the parabola, the ellipse, and now the hyperbola. When do we get a hyperbola? When we slice it in such a way that it actually penetrates both of the cones and will have a very symmetrical outcome. Basically, it almost appears like having a pair of parabolas, okay? They're not quite definitionally parabolic in trajectory. They have their own unique definition that is hyperbolic. So let's go to our next slide where we analyze the definition of a hyperbola. So first, I'd like to begin, like we did in our previous videos, by looking at the two possible orientations for our hyperbola. We could have two hyperbola which are opening left and right or up and down. So we have names for that. We would either have a horizontal transverse axis, transverse meaning cutting through, so that transverse axis that you see in the first picture in blue on the left side of the screen there, or actually more like the middle. That transverse axis is the line that is cutting through your vertices, your foci, and your center. Very similar to your major axis. In fact, it's so similar, it actually stops at your vertices, if I'm being very specific here. So stopping at your vertices, it would have a total distance from one vertex to another, that is the distance of the transverse axis, of 2a. Where remember what A was, just like with ellipses? A was that distance from your center to each of the vertices on the transverse axis. So for example, here is one vertex, here is another vertex on the horizontal transverse axis. Notice in the other picture on the right of your screen, the far right, you'll see a hyperbola which opens up and down instead. We would say that it has a vertical transverse axis, meaning the line that connects these two vertices is a vertical line, okay? And again, that vertical transverse axis has a total length of 2a, because a is your distance from your center to each of your vertices. Notice also that just as b was defined as the length from your center to the endpoints on your minor axis for ellipses, now b is also critical, but it's not going to help you get points on the trajectory this time. So that is a distinction. b will actually give you points which if you were to go up and down b units, in this case when we have a horizontal transverse axis, if you went up b units here or down b units there, so the length there would be 2b, you would actually get, eventually, using the idea of b over a, so remember that slope was rise over run, so in this case, b over your run, which is your a, this would be the slope of your asymptotes, the slope of your asymptotes. What are you talking about, you might be thinking? Why do we need asymptotes? Well, what we've figured out so far is if we have a hyperbola, which is opening left and right, we know the two endpoints, the most extreme points, are those vertices, right? But we don't know how wide or how narrow to make those curves. And so in order to determine the width of those curves, we need a constraint. We need something to approach. And the two lines which will constrain our curves are called those asymptotes. We've dealt with asymptotes before with rational functions and exponential and logarithmic functions. So nothing new as far as asymptotes, but what we're going to be needing to find is the equation of these asymptotes. So how do we do that? Well, if I want the equation of the first asymptote here that has a positive slope, what I would need to do is use my slope of rise over run, so up b and over a, and I would get to this location here in the corner of that little box they've created. I could have also gone down b, so go down and left a, and I get another point in the corner of that box. And now I could connect those dots, and I would form one of my two asymptotes. Interesting, or maybe you think weird, okay. Similarly, I could have gone from my center up b and then left a to get this point, let me grab my pen, to get this point in the left top corner. Or I could have gone from the center down b and right a units to get to this point in the right-hand bottom corner of that box. Connecting the center and those two locations, carefully, sorry about that popping up each time, we would get our second line that has the negative slope, negative b over a. So I really have a positive and a negative line there. I have a positive and a negative slope of b over a. Now similarly, if I was doing a hyperbola, if I was graphing a hyperbola, which is opening up and down, in other words, having a vertical transverse axis like the picture on the right, I similarly could have gotten my two asymptotes by traveling a rise this time of A, so this time the slope would have been, let me grab another color so you can see me. In this case, the slope of these asymptotes would have been go up your rise of A and then run B, right? So A took you to your vertices, so we had to go up and down to get to my vertices if it was a vertical transverse axis. So again, we would have a positive and a negative slope of A over B this time. And now we would be able to draw our two asymptotic lines with the appropriate slope of A over B being positive or negative to get our two different lines. And we would also notice that it goes through the center, which is HK. Okay, with that said, you could then sketch your hyperbola correctly. So notice that's what we've done here. We've said, okay, now that I have my my vertex here, and I know it has to approach this asymptote, I can now draw my picture, right? Going through my vertices, approaching my asymptotes. Okay, so there's one hyperbola. Another hyperbola going up and down would approach those asymptotes. So something like that, oops, and something like that. Okay, so you could draw your sketch. Okay, now what is the formal definition of a hyperbola? Remember with an ellipse, we said that to be on the elliptical trajectory, you had to be at such a point where if you measure the distance from that point to two different fixed points within the vertices, within the ellipse, that if you added those distances, whatever sum you got better be consistent as you go across your elliptical trajectory. Turns out that while the sum was constant for the ellipse, the difference will be constant for the hyperbola. So let's look at our formal definition here. When we say a hyperbola, to be on the trajectory, you must be a point where if you took the distance to the two fixed points, which are again on the they're beyond the transverse axis, I should be more clear, like a foci here and a foci here. So we'll call this like focus 1. Can't really see that color. Let me get you a better one. How about we do orange? So like focus 1, I'll call that focus 2 actually. Focus 1 on the left, focus 2 on the right, just to be consistent. Okay, so if we have these two foci, if we were to take a point on this trajectory, on the hyperbolic trajectory on either side, and we were to measure the distance from that point to this fixed point called a focus, and from this point to this fixed point called a focus, focus 1 and focus 2. Say we got one distance of 8 and another distance of 2. It turns out that if I subtract, meaning I get the difference of those distances, 8 minus 6 would be 2, but maybe I did 6 minus 8, right, and I got negative 2. That's why we write absolute values, since it matters the order in which you do subtraction. You'll get different signs. So it doesn't matter if you do the positive or the negative, basically. If the absolute value of those differences is 2, then what would happen is if I picked another point on the pathway, it doesn't matter if now I get 9 and 7 as my distances. When I subtract them, I have 2 still. So you should be getting the same exact difference in distances to those fixed points. So that's the definition, which means that the equation will look very similar to the elliptical equation. The only difference, no pun intended, is that now we have a difference. So let's take a look at that right here in our equations. Let me grab my pen. Now we have a difference in our equations. We have an x squared term over a number minus a y squared term over a number, and vice versa, equaling 1, where hk is still my center. But now here's something that is new. While c is still going to be our distance, let me grab my orange color here. C is still your distance from your center to each of your foci, and it's actually, I should say beyond, I don't know why I said on. It's just beyond your transverse axis, so a little bit bigger than the distance of A, okay? So just beyond your transverse axis. Well, that is still consistent. C is the distance from your center to your foci. That's the same definition as it was for an ellipse. Now though, because C has to go beyond your vertices, it has to be bigger than A. So instead of subtracting A squared and B squared, we will be adding A squared and B squared, and that is how we'll get our bigger C value. There's one other fact here that's different from ellipses though. So if this is for hyperbola, you want to make sure you practice both hyperbola and ellipses side by side in your homework and in your studies so that you really can see the difference in their equations here. They're similar yet different. So for hyperbola, c squared will equal a squared plus b squared, but the equation in standard form of a hyperbola will have a difference, not a sum, in between the squared terms x and y. So that's interesting. One other interesting point to note is that for ellipses, remember how A was always bigger than B in order for it not to be a degenerate, in order for it not to be a perfect circle, for it to truly be a degenerate circle, one side had to be bigger than the other, and so A was our longer side on our major axis? Well, that doesn't have to be true for a hyperbola. It turns out that A and B could be equal. If that were the case, all that would change here is that your slopes, A over B or B over A, depending on the different orientation, would be 1, wouldn't they? And we can draw a line with a slope of 1, up 1, right 1, down 1, left 1, etc. So we're allowed to have A and B being the same for hyperbolas. Also, B could be bigger than A, right? We could have 3 over 2 or 2 over 3 as our slope. It doesn't matter. We'll just have a slightly different picture, okay? So we are allowed to have A or B bigger. So the question becomes, well, how would I know by looking at an equation whether my hyperbola are opening left and right or up and down? And that is a good question to ask. You might not have it right now, but eventually you'll start asking that question. How do I know which way it's going? And the way you'll know is by which squared term is positive. In other words, which one does not have a negative sign in front of it. If x is squared and it doesn't have the negative sign, so if it comes first, but the y term has the negative sign, then we would say we're opening left and right. In other words, we have a horizontal transverse axis. On the other hand, if the y term is first, if it's positive, and the x squared term is negative, then we would say that this hyperbola is opening up and down. It has a vertical transverse axis. So the key is who is positive, right? And who is negative. If you're the positive term, the positive variable, that is the indication that you're opening in that direction. Also notice here that I've written out your equations for asymptotes. You don't have to memorize this. There's nothing new to memorize as long as you know the equation of a line, because these asymptotes are just that, they're lines. Remember how we can write equations of lines? Well, one way is the y equals mx plus b way, right? Slope-intercept form. Great for graphing, but not super helpful as you get into calculus. It turns out the more helpful form of a line is the point-slope form. Do you remember that? Where you have a point x1, y1, and a slope m? That's right, y minus y1 equals the slope m, parentheses x, minus x1. And it's directly derived from the slope equation. You can check that yourself if you solve, if you move things around in the slope equation. Okay, so now we're looking at the point-slope form of a line, and I'm claiming that this is the way we're actually writing the equation of these asymptotes pretty easily, because we have a point on each of these asymptotes, and that point is the center. So if we were to replace x1 with h and y1 with k, we would have the equations above, right? We would have our x and our x replaced with h and our y1 replaced with k. Notice also that the slope will either be a over b or b over a, depending on if a is going up, because it's a vertical transverse axis, and down, or left and right. If it's going up and down, it's a rise, and if it's going left and right, it's a run. But slope is always your rise over your run. So rather than memorize a over b or b over a, I just look at the picture as I put down my information on my graph, and I say, okay, what is my rise and which is my run? So if a is your rise, b is your run, and vice versa. Okay, and finally to find c, if you were interested for the actual graph, you would just use this notation. A squared plus b squared gets you to c squared, which then square root, and you have your foci location. So that is a lot of information again. I really encourage you, just like in the previous videos, pause it, make sure your notes are very clear, email me if you have questions about any of this stuff, and then start the actual problems, because if you don't know the definitions and what A, B, and C stand for, you're not going to have a chance. Okay, so let's head over when you're ready. Excuse me. So in example 1, we are given an equation, x squared over 4 minus y squared over 25 equals 1. And we're being asked to find the vertices and the foci of the hyperbola below. Again, out of this section, how would you know that this equation is a hyperbola? That's right. You have two squared terms, so it can't be a parabola, and they are being subtracted. So if you have two squared terms being subtracted, that is the clue. This is a hyperbola. Regardless if your denominators are the same, big or different, we don't care. As long as the two squared terms are being subtracted, this is a hyperbola. What else do we need to figure out? Well, we could see the center quite obviously, I hope. Now be careful, the center is always hk, and h is always associated with the x value and k with the y value. In this case, it's obvious because it's 0, 0, right? But in a few examples that you'll run into, you might have the y squared term first and the x squared term second. And it's really easy to switch the order of h and k if you're not paying close attention. So just a reminder to pay close attention there. Other things to notice. We need to know how this is oriented. In other words, are my parabolas opening up and down, or are they opening left and right? And to determine that, do we look and see who has the bigger number, or what else? That's right, we look at who's positive. There you go. So we say, who's the positive term? This time, x is the positive term, because there's no negative sign in front of it, meaning that this is a horizontal transverse axis. When you learn something, it usually helps to write it out as you're learning it, okay? Something about kinesthetic learning, okay? So we want to make sure we understand this is a horizontal transverse axis because the x squared term is the positive term. Notice you might have been tempted, you don't have to admit it, but you might have been tempted to think that this was a vertical transverse axis because the bigger number was under the y term. And that is the logic you would use if this was an ellipse. But because this is a hyperbola, we don't look for who's the bigger number in the denominator, but rather who is the positive term. Okay, so we have the fact that it's horizontal in nature, meaning something like this is happening. Okay, that's the idea. Since it's centered at the origin, so like here's the origin, something like this is going on. Okay, so we have the basic idea here, but we're asked to find the vertices. So I need to find this point and this point, that's like vertex 1 and vertex 2, and I could do that if I knew what letter, A, B, or C. That's right, we need A to get to my vertices. So to get to those vertices, I need to find A. But remember, we know A squared is the term under, not the bigger number, but it's the term under the positive term. So A squared must be 4, meaning that C squared is actually the bigger one, B squared is the bigger one this time, it's 25. I was jumping ahead of myself with C squared. We'll find C squared in just a moment. Okay. So if we know that A squared is 4, do we know now what A is? Yeah, A is 2. So I'm actually going 2 units to the right and 2 units to the left to get to my vertices. So I could just write plus or minus 2, comma 0 as my 2 ordered pairs, or negative 2, 0, comma positive 2, 0. Okay, so we have our vertices. Now, B, again, is helpful if I want the equations of the asymptotes. So if I wanted to get my asymptotes, I'll just write it up here if you're curious, if you wanted to do more than was required, but really practice and learn the skill of graphing. Your asymptotes would have the equation, again, your point-slope form, y minus y1, but your center is just 0, 0, so y minus 0, equals plus or minus my slope, which is my rise over my run, times x minus x1, where x1 is your h value of your center, which is just 0. So that looks a little bit clunky. We could clean up those zeros, couldn't we? So we just have now the slope next to x there. Okay, so y equals positive or negative, whatever my slope is, times x. Okay, so how do we figure out the slope? Well, if my A was going left and right, A must be my run, because it was going left and right. It was horizontal in nature. So B must be my rise. That's right. So my rise is actually the square root of 25, which is 5. So if B is 5, I now know that my slope here is 5 over 2. So y equals plus or minus 5, my rise, over 2, my run, x. And now I could draw those lines. I'd go up 2 from the center. So my rise was, up 5 from the center, 2, 3, 4, 5, and over 2, there's a point, or down 5 from the center, over 2, there's a point, or down 5 and left 2, or down 5 and up 2, up 5 and left 2, I should say. And now I could connect those dots. It's kind of ugly on my sketch here, bear with me. And now we could draw a better picture. So instead of my rough sketch earlier of my hyperbolas, which were opening left and right, now they're more like this, really. That's a better sketch. So by getting those asymptotic lines, we're able to get a better idea of what's going on. They weren't quite as narrow there, a little bit wider. Again, we weren't asking you for a picture, but if you wanted to get the asymptotes, you'd be able to get a better sketch. What we were asking you for was the location of the foci. So how do we find the foci? What letter do we need? That's right, just like with ellipses, you need the letter C. So in order to get the C, you have to remember the relationship between A, B, and C for a hyperbola. And what I like to remember is if the equation was a minus between the squared terms, then the relationship in the relationship of a, b, and c is the opposite. So it'll be a squared plus b squared. So if you can remember those opposites, you'll be having an easier time of things. So a squared plus b squared, we have that information at our disposal. We would now know that c squared then is just a squared of 4, b squared of 25, so that's 29 when I add them together. In other words, c is the square root of 29, which is nasty. It's between the square root of 25, which is 5, and the square root of 36, which is 6. So something between 5 and 6, so somewhere out here, 2, 3, 4, 5, 6, somewhere in here is my foci, or my foci I should say. So 2, 3, 4, 5, and 6, somewhere in there, my other focus. Okay, so we could keep ourselves honest in our picture, because if we were to take the distance again from any point on the trajectory to this fixed point and to this fixed point and subtract the differences, take the absolute value, it will remain constant no matter which point on the path I pick. As far as the actual locations as ordered pairs, what would they be? Well, if we went left and right from the center, it would be positive and negative, square root of 29, comma 0. Again, I want to point out that this example is actually an easy one because we've centered our hyperbola at the origin. Had it been anywhere else, you would have to carefully start at those x or y values and travel left or right or up or down, depending on what orientation it is, and then get your new locations. So you have to do a little bit more work when it's not quite the origin. Okay, at this point, we've looked at one example which has standard form. What if we have something a little more complicated? So let's take a look at our next example. So we have y minus 1 squared over 9 minus x plus 1 squared over 16 equals 1. It says, could you analyze and sketch the graph of this conic section? It happens to be a hyperbola, but you should know that because they're being subtracted, right? Okay, first things first. What center do you have and what type of orientation is it, right? Your center is always HK. H is associated with x, and it's always counterintuitive when it's in parentheses being added or subtracted. So what is my center? See if you can write that down yourself. What is your center? That's right, it should be negative 1, comma 1. So there's my H, and there's my K. But it's always counterintuitive in parentheses there. So I could actually go to my graph and start at negative 1, so left 1, and positive 1, up 1. There's the location of the center. Now from there, do I go up and down to get to my vertices, or do I go left and right? That's what I need to determine next. What kind of orientation is it? To determine that, what do we look at? That's right, who is the positive term for hyperbola? In this case, y. Y is the positive term, which means I have a vertical transverse axis. I'm opening up and down, not left and right. So if I'm opening up and down from the center, I will be going to change the y values. I'll be going up, adding, and I'll be subtracting from the y value of the center, which is k is 1. So I first need to find out my a and my b and my c, and then I can start finding the locations of the vertices, the foci, and the asymptotes. Okay, so what do we know? Well, if it's truly a situation where we have a vertical transverse axis, and under our first term, the positive term is a 9, we now know that that's a squared, isn't it? So if a squared is 9, what is a? Yeah, a is 3. Remember, a will take you to your vertices, won't it? I like to write that down as I'm learning things, right? What else do we know? Well, we know b squared is the other number then. So b squared must be 16. And if b squared is 16, then b must be the square root of 16, or 4. Now this will help me with my slope, right? So in my slope, we need to figure out who is the rise and who is the run. Well, since it was a vertical transverse axis, we are going to be going up and down from my y value, 3 units in each direction, up and down, to get to my vertices. So for example, if I went up 3 units, 1, 2, 3, I'd be here. Well, isn't that the point, negative 1, comma 4? You just add 3 units to the y value of 1 and you get 4. What's the other location if you went down 3 units from the center at negative 1, 1? 1, 2, 3. Isn't that at the location negative 1, negative 2, which you could have gotten by subtracting 3 from the y value 1? You get a y value of negative 2. So there are my 2 vertices in my picture. So this is like vertex 2, vertex 1. Okay, so we now know how it's opening up and down, but the question is, if you're doing a sketch, how wide or how narrow to make those curves? And that's where we need the asymptotes, the slope of the asymptotes. So if my going up and down resulted in getting to my vertices, which is rising or falling, right? That means that A must have been my rise. So in my slope, I could write my rise was 3 units. So this was my rise. If your rise was 3 units, then you know that the run must be the other letter, B. So my run must be 4 units. Now I know the slope of my asymptotic lines that I'm approaching. So for my equation of the asymptotes, we typically say y minus y1, but here the y value of your center that you're going through is 1. So y minus 1. We'll need a positive and a negative asymptote, so we'll have plus or minus our slope, which was the rise of 3 and the run of 4. And then x minus our x1 value, which in this case, x minus the h value of the center. So x minus a negative 1 is x plus 1. And again, you could rewrite that in slope-intercept form if you prefer, but that is sufficient for your 2 equations of your asymptotic lines. But practically speaking, we should be able to put this on our graph now. We rise 3 from our center, and we're at our vertex 1, and then we run 4 in each direction, left and right. 1, 2, 3, 4. I'm landing at the point, looks like 3, 4, okay? Or if I started at that same vertex and went the other direction, so I went up 3 from the center and left 4. 1, 2, 3, 4, and I'm at this location. Or I could have gone down 3, left 4, and get this location. Or down 3 from the center and right 4 and get this location. And you could definitely plot those carefully on graph paper and in your My Math Lab homework. Now you could sketch the lines that go through that center and through those locations in the box's corners, and you get your asymptotic lines. Again, what is the purpose of the asymptotic lines? They tell you how wide or how narrow to make your actual hyperbola's graph. We know we have a hyperbola that goes through the vertices and approaches these asymptotic lines. So this hyperbolic trajectory has one piece up here like so, and one piece down here like so, high degrees of symmetry. So you could be a point on the hyperbolic trajectory in either location. One other thing to note is the foci, to keep yourself honest, right? What actually defines this hyperbola in the background, what's happening? And so to figure that out, we need to know our foci. And to get to our foci, we use C. Well, what was C? Remember, for a hyperbola, what is the relationship between A, B, and C? That's right, it's right below. C squared equals A squared plus B squared. So notice there's a plus here when we have a difference in our original equation. They're opposites. Okay, so A squared, well, that was just 9. B squared, that was just 16. In this case, we get a nice number. It's 25, so C must be its square root, which is 5. So if C is 5, that takes me to my foci. But be careful, it's not from the origin. It's from the center on the right beyond the transverse axis, beyond the vertices on the transverse axis. So we'd start at our center, and we would go up and down 5 units from the y value of 1 at the center. If you go up 5 units, for example, 1, 2, 3, 4, 5. So that is the location of -1, 6. What's the other location? Well, we could have gone from the center down 5 units. The center was at -1, +1 for y. So that's going to be 1, 2, 3, 4, 5. So your new location, when you subtract 5 from the y value 1, is -4. So the point would be at -1, -4. Okay, those are your 2 locations for your foci. So let me just put those on the graph a little cleaner with orange here. So there's one focus, one of the foci I should say, at -1, -4, and there's another one of your foci at -1, 6. Okay, so that would keep you honest, right? You could then find the distance on any point on the hyperbolic path that you're proposing to be on your path, find the distance to each of the foci and subtract them. That difference in the distances should remain constant. Okay, we have one more example. This time it won't be in standard form, so see if you can remember what to do. It says, can you write the equation in standard form for the hyperbola described below? X squared minus 2y squared minus 8y equals 12. Okay, so how do you know it's a hyperbola one more time besides the fact that they told you? Well, you have 2 squared terms and they were being subtracted. If they had been added, what would this have been? An ellipse, good job. So this is in fact a hyperbola for that reason, those reasons. Next thing we did was try to complete the square. But where? Notice I don't need to complete the square for the x variable because there's only an x squared. There's no other variables there. So this time you'll only need to complete the square for the y variables. Take a moment, pause the video, maybe go back to the ellipse video, see if you can do that on your own, and then we'll come back and check. Okay, so did you do the following? You notice that for the y terms, we needed to factor out the leading coefficient of -2, and we got y squared, and then we got a positive plus 4y. And then we left some space to complete that square, equaling our constant of 12. If you did that, great job. Keep in mind, most of the time you'll have another constant that you'll have to first move over, right? Now, what did we have to do after we had factored out that negative? We had to be really careful with it, right, the -2. Because when we complete the square here, we take half of 4, which is 2. We squared it, which was 4. So we really added a 4 in parentheses. But if you remember from our previous videos, we said that you had to be careful here because the net impact, the real result of putting a 4 in parentheses, was eventually that -2 multiplies by it, meaning we've really created a -8. So the net result was really we subtracted 8 on the left, -8. So if we subtracted 8 on the left, we have to also subtract 8 on the right to maintain the balance of this equation. Otherwise, we've changed the equation illegally. Okay, once we've done that, the whole purpose was we've created a perfect square trinomial, which can be factored. And we're getting one step closer to standard form. So now we would have x squared minus 2 copies of what factorization? Yep, y plus 2 to the second power. And the collateral damage of 12 minus 8 was just a 4. You are one step away from being done with this problem and with this video. Okay, so what do you do next? That's right, divide everything by 4 because you would like it in standard form. So divide by 4 here, divide by 4 there, divide by 4 there. Your final equation becomes x squared over 4, that's right, minus parentheses y plus 2, close parentheses, squared over 2, because 2 over 4 reduces to 1/2, equals 4 over 4, which is really 1. So x squared over 4 minus y plus 2 squared over 2 equals 1. This is your equation in standard form, which you could now use, if you would be so inclined, to graph a hyperbola whose center was at 0, -2, who has a horizontal transverse axis where a squared is 4 and b squared is 2, and c squared would be 4 plus 2 or 6. And you could then get your foci, your vertices, and draw your asymptotes and make a picture. Okay, at this point we've finished hyperbola. We finished all of the conic sections. I would really encourage you to make sure you try practicing each conic section with another one side by side so you can see the difference in their forms, and make sure you know how to graph them, write their equation, and use them to model real life examples. All right, if you have any questions, you can email me. Good luck practicing. Remember, math is not a spectator sport. See you next time.